Okay, so let's start today's lecture. Okay, so in the last lecture, by the end of last lecture, we have been reviewing our method of solutions of higher order equations, linear equations. So basically, all these ideas that we've been talking about so far is just a very simple idea. Is that you have an nth order, suppose you have an nth order differential equation, then you're going to kind of use this transformation. So you let the solution to be e to the power of RT, and then there's therefore the equation for y is turned to an equation for r, and this was an algebraic equation. So this is actually, so the above equation is a differential, right? So differential equation, right? So this is a differential equation, and this is an algebraic equation. Right, so this is an algebraic. So you have to turn the differential equation into an algebraic equation. Okay, so now this correspondency is actually the correspondency between y and r. Okay, so it's the correspondency between y and r, and therefore you this transformation is going to just give you a solution. Okay, so and from which you can build the complementary solution as well as the general solution. Okay, particular solution. So the key point here is to do this transformation, right? So the key point here is to do this transformation, namely you transform the solution y to the solution r. Okay, so as long as you have this transformation, there's a 1-1 correspondency between these two types of solutions. On one side, it was a differential equation, and you want to solve it during this class. Okay, so but on the other side, it becomes an algebraic equation. Okay, so and you know how to solve algebraic equation. So this is like a method that can be generalized to a very general idea. Okay, so this is a method that can be generalized to a very general idea. So the idea is that between differential equation and algebraic equation, there is a transformation like this. Okay, so you transform y to r, or you transform r to y. Correspondingly, that you transform between y and r. That means you transform between differential and algebraic equation. Okay, so this philosophy extended. Okay, so has been thoroughly extended to the current chapter, and that's the major topic we're going to talk about in this chapter. That we call it Laplace transforms. Okay, so let me remind you that Laplace transforms is significantly harder. Okay, so to understand. Okay, harder to grasp than the previous chapters. So that I would like you to spend as much time as possible to focus yourself on this topic. Okay, so that's the this point. Okay, so what is a Laplace transform? Okay, so a Laplace transform. Okay, so let's say Laplace transform. Okay, so Laplace transform is a transformation. So it's kind of more general than this R, because R is just a number. You just transform the function to a number. Here, the Laplace transform is transforming a function. Okay, so let's say you transform a function f of t into, so we're going to call this a Laplace transform, right? So, and into a capital F of s. So that's going to be the transformation. So you can see that it is more general than what we had before. Before it was like r, right? So it's transformed to y. Well, y is like a function. Well, it's function, but r is just a number. So that was a kind of a simple situation. But here we're going to talk about a very general situation that you're going to have a function f of t. Under the transformation, it's going to have become the function capital F of s. Remember, the argument t and s are different. So that means on one side, you have a function of t. On the other side, you should look for a function of s. So the arguments of the functions are completely different. Okay, so you can think of Laplace transform as a mirror. Okay, so let's say somebody is standing in front of the mirror, right? So this is the Laplace transform. Then it's going to be transformed to his image inside the mirror, right? So that's this is your mirror, right? So let's say you can think of this Laplace transformation as a mirror. It transforms the image of a person to its mirror image, right? So that's going to be the situation for the Laplace transforms. Okay, so now how does the transform be defined? Well, the definition of this transformation is telling you that Laplace transform of f. Okay, sometimes we write LF of t, but this is a function of s. So this definition, this notation is kind of super complicated. So sometimes in order to make things simpler, we will just write LF of s, or maybe we'll just write LF. Is that good, family? Okay, so that's a capital F of s is this function. Okay, so now this function is to be defined by the integral from 0 to infinity e to the power minus s and t multiplied by f of t dt. So that's going to be the transformation. Is that good, family? Okay, so let us look carefully at this transformation and see what it does. Okay, so now first thing is that, well, this is an integral. Okay, so the integral, okay, so the integral is with respect to t. So you have the t variable here, you have the t variable here. The t variable is being integrated. Is that good, family? Okay, so you're going to integrate the t. So therefore, the integral is resulting you a function of s, because the s is the argument here that you result in a function of s. You don't have the function t, because the t is being integrated from 0 to infinity. So that's an indefinite integral. Is that good, family? Okay, so now the second thing is that let's say you want the integral to converge, right? So that means you would like to have the integral from 0 to infinity e power minus s and t multiplied by f of t dt. You want the integral to converge. When is the integral convergent? Well, you can see that if s is negative, let's say equal to 0, let's say s is less than 0, then you're going to have an exponential blow up. So because the integral 0 to infinity e power alpha t dt, that's going to be infinity if alpha is greater than 0. Is that good, family? Right? So that's going to be the scenario. So if s is less than 0, you definitely won't have the situation. You won't have a good convergence for your integral. So therefore, at least you have to assume that s is greater or equal than 0. Is that good, family? Right? So because you just want the exponential to kill any possible growth of the function f. Is that good, family? Okay, so that means on the image side, the argument s has to be at least non-negative. Is that good, family? Okay, so that's going to be very important. Okay, so you must remember. Okay, so you must remember the shape of this Laplace transform. Okay, so you must remember the shape of this Laplace transform in terms of its integrand. Okay, so now you can see that the integrand has an easy way to memorize it. It's just our university name, right? So e power minus s and t, then multiplied by. So you just remember this part is the contribution from the university, right? Then it's multiplied by the original function that you would like to transform. You integrate with respect to that function. You leave the other component, okay, as your parameter s, and that's f of s. And you have to keep in mind that s is something positive. Is that good, family? Okay. Now some people is going to ask, what's the relation between this one and the original one? It was telling you that r is being transformed to e power rt. Well, you can see this exponentials is the common feature of these transformations. So that means that this Laplace transform is like a much more general idea than the previous one regarding the characteristic equations. Okay, so it is kind of in a certain sense related to that characteristic equation, but it is a much more general transformation. Is that good, family? As I said, you always think of Laplace transforms as a mirror, right? So that means the function f is standing in front of the mirror, and then under the transformation, so that you think of this as a mirror, right? So that's inside the mirror, you're going to see your image, which is the capital F of s. Is a good, family? But this mirror might not be like a plain mirror, right? Like you see in every day, but it might be deformed, so that the capital F is not exactly small f. Okay, so now this lecture, we're going to kind of give you examples of Laplace transforms. Okay, so let us try to practice examples of Laplace transforms. Okay, so let us try to practice examples of Laplace transforms. Okay, so we're going to see several examples. So for example, what is the simplest type of function f of t? Remember, what we are doing is that you start from a small function f of t, small f. You want to transform to capital F. So the question is, what is the simplest type of function you have in your mind? Well, the simplest type of function you have in your mind should be a constant or just one. So that's a simple function f of t is just equal to 1. So that we are going to see that capital F of s is the Laplace transform of 1, right? So an argument s, or maybe you just say Laplace transform of 1. So that's going to be by definition. So you must follow the definition. Definition says that it is an integral from 0 to infinity, e power of the universal name, s and t, and then multiplied by the f. Well, f is equal to 1, so that's just 1 of the dt. Is a good family, right? So integration is with respect to t. So that's going to be just a very simple integral. It's just the integral from 0 to infinity e power s and t dt. And what's that integral? Well, that integral is going to be just 1 over s e power minus s and t, where t is equal to, so we're going to have a minus sign here. T is equal to infinity minus t equal to 0, right? So that's going to be just because when t is infinity, so you have to be careful here. 1 over s e power minus s multiplied by infinity, right? And then it's kind of going to be plus 1 over s e power minus s multiplied by 0. Is that good, family? Now this one is clear, right? So this is just going to be equal to 1. What about this one? Well, remember, as we said, that you usually set s greater or equal to 0. Okay, so in fact, we are going to, in order to agree with my definition, I will just set s to be positive. Okay, so you can, I mean, let's say s is just assumed to be positive. Okay, so I won't be bothered with the case where s is equal to 0. Okay, so that's just positive. So that means here, you are going to have s is just going to be positive. Is that good, family? Okay, so s is just going to be positive. Now, if s is positive, a positive number multiplied by infinity raised to an exponential with a minus sign is just equal to 0 because that's the limit. So basically, for any s greater than 0, the limit of u going to infinity, e power minus s multiplied by u is just equal to 0. Is that good, family? Okay, so we're going to just use this side effect. Okay, so we just use this side effect. So that means that after this integral, you won't have this term, and so therefore you just have 1 over s. Is that good, family? Okay, so we reached such a nice conclusion that Laplace transform of 1 of s is equal to 1 over s. Is that good, family? It is not going to transform. So you might think naively that it is going to transform 1 into 1, but not necessarily so. It is going to transform the function 1 into the function 1 over s, where s is assumed to be positive. So the domain of definition of your image function is going to be super important. Okay, so you cannot say that I do a Laplace transform without specifying the domain of definition of the image function. So that's going to be super important. Is that good, family? Okay, so it's going to transform 1 to s. Now let us look at some further example. Okay, so for example here, it says, can you find Laplace transform of an exponential function? So that means we're going to say that we're going to talk about f of t is e power of at, where t is greater or equal to 0. We're going to consider Laplace transform of f. Okay, so let's say is equal to capital F. Now, how do you calculate it? Well, you're going to calculate capital F of s is the Laplace transform of e power at. So you're going to do something like this. Let's say a function of s. Okay, so then this means that this is the integral from 0 to infinity e power minus s and t, and then e power of at of dt. So that's going to be your scenario. Okay, so that's going to be your scenario. So that's going to be the case that you're going to see that this integral is nothing but the integral from 0 to infinity e power minus s minus a of t dt. So it's going to be something like this. Is that good, family? Okay, so therefore, let me say, what about a positive? Suppose a is a positive number. Okay, so suppose a is a positive number. Then you can see that the integral is actually, so the integral is actually calculated as minus 1 over s minus a e power minus s minus a of t, where t is equal to infinity and t equal to 0. So you just calculate this integral. And if you calculate this integral, it's 1 over s minus a e power minus s. Okay, so e power minus of, okay, so minus of s minus a of t, where t is equal to infinity. So you're going to replace the t by the infinity here, and then plus 1 over s minus a e power minus s minus a multiplied by 0. Is that good for everybody? Okay, so that's going to be scenario. Now you can see that's very similar to what you had before. If you want the first integral to be 0, you have to set s to be larger than a. Is that good for everybody? If s is larger than a, s minus a is something positive, then this is going to be 0 because you have an infinity. So that in that case, you can see that if a is positive, okay, so if a is positive, then when we define f of s, we even need s to be greater than a. Is that good for everybody? Okay, so, and this is non-trivial because s is greater than a than positive, which means that s is not just positive. So this is, suppose this is 0, this is a, then it's not just a positive for like larger than 0 is not enough, right? So larger than 0 is not enough, but it is larger than a, so this is s larger than a, right? So let me put a better picture here. Okay, so this domain is like s larger than a. Right, so and this domain is s larger than 0, right? So originally we were saying that Laplace transforms is always defined on s larger than 0, this domain. But now for this particular problem, you can see that you're even restricted to s larger than a. It's much smaller domain depending on how large is the a. So that kind of is very important. Okay, so when you're on an exams, okay, when you're on an exams, you're calculating the transformations. Like here, you're calculating, you're given a function. I ask you to transform as a Laplace transform. You must calculate not only the resulting function, but also the domain of definition. Okay, so that means you must also specify which domain of definition gives you s, right? So the s must be restricted to a certain domain of definition. And this will be 0, this one will be 1. Okay, so this one will be 1. So the result is just 1 over s minus a, but you must specify that s is larger than a. Is that good for everybody? Okay, so that's going to be very, very important. Okay, so that's going to be very, very important. You must specify the domain of definition of the resulting transformation function. Okay, transformation function. So that's going to be the important thing. And you can also see that, let's say here we assume a is greater than 0, but let's say if a is equal to 0, the function is just going to be equal to 1. In that case, s larger than a becomes s larger than 0, and the resulting function is 1 over s. It just agrees with this one, right? So basically, we're saying that Laplace transform of 1 is the Laplace transform e power 0 multiplied by t. It's 1 over s minus 0 when s larger than 0. It's just 1 over s when s larger than 0. So that's going to be like the second example reduces to first example. Is a good family. So we've got like two different examples. The first one says Laplace transform of 1 is equal to 1 over s. The second one says Laplace transform of e power of at. Okay, so it's just equal to 1 over s minus a. In both scenarios, we have to specify the domain of definition of the resulting function. Is that good family? I must point to you here that I have been abbreviating the definition in the sense that I consider Laplace transform of 1 and Laplace transform of e power of at. I didn't write the argument s out, but I just write this function as being transformed. Is that good? You must understand that what I'm saying here is that it is actually Laplace transform 1 with the argument s and Laplace transform e power at with the argument s. Is that good, family? Okay, so but for simplicity, I'm not going to write down this argument for the transformed function, but you must understand there is an argument. Is that good, family? Okay, so that's going to be the Laplace transforms of these two functions. Okay, so we have seen like two examples so far in today's lecture. Okay, so now we're going to kind of work with one more example. That's just saying that what is the Laplace transform, right? So what is the Laplace transform of the following function? 5.e power 2t plus 3. So let me say 5.e power 2t plus 3. Okay, so let me just use this function. Okay, so I would like to consider this function. Okay, 5e power 2t plus 3. Okay, so let's say this one. Okay, 5e power 2t plus 3. Okay, so I want to consider the Laplace transform of this function. So then how should I do it? Well, by definition, right? So by definition, then you can do an integral from 0 to infinity e power minus s and t and 5 e power minus 2t plus 3, let's say dt. You want to just doing this integral. Is that good for everybody? Okay. So, but once you do this integral, you can see that indeed because the integration is a linear operation. So which means that you can simply write this one as 5 times the integral of 0 to infinity e power s and t multiplied by e power minus 2t dt plus 3 times the integral of 0 to infinity e power minus s and t multiplied by 1 dt. Do you agree with me? Why is that the case? Well, because the 5, right? So the 5 can be multiplied into here. The 3 can be multiplied into here, so that you get 5 plus 3. And because the plus can be splitted, right? So because the integral. So basically, we're using the fact. Okay, so we're using the fact. Okay, so basically, we're using the side fact that integral of alpha of f plus beta of g is alpha of the integral of f plus beta of the integral of g. So that's going to be like the linearity of integrals. Okay, so that's going to be the linearity of integrals, right? So we're just using this fact, you can just split everything. Okay, so you can just split everything. Now, once you split it into something like this, do you have to really calculate these integrals? Well, the answer is no, because this is 5 times what? E power, so this is nothing but Laplace transform of e power minus 2t. Because you're treating this function as your f of t, then you're going to have the Laplace transform. Remember, the Laplace transform has a formula. It is just equal to e power s and t multiplied by ft dt. So that means with this transformation, this is the 5 times the Laplace transform of e power minus 2t, and then plus 3 times the Laplace transform of 1. Is that good for everybody? Okay, so let me say, let me just ignore these brackets. So that's going to be very simple. Okay, so because e power minus 2t is 5 over s plus 2. Remember, here a is equal to minus 2, like in this case. So you want to use s minus 2. And then 3 is over s because 1 is transformed to 1 over s. Is that good for everybody? Okay, so in this example, we didn't do any integral calculation. Like what we have here, you have to find the antiderivatives. Here we didn't do anything related to the antiderivatives. We just split the integrand into 2 integrands, and therefore we used the example 1 and example 2. The first 2 examples just immediately give us an answer. Is that good for everybody? Okay, so this is going to be a very important phenomenon that sometimes we're going to call it the linearity of Laplace transforms. Okay, so the linearity, okay, so of Laplace transforms. Okay, so linearity of Laplace transforms. What is the linearity of Laplace transform? It means that if you transform the function alpha times f plus beta times g, you're transforming these 2 functions. So f is equal to f of t, g is equal to g of t, and alpha beta are 2 real numbers. In that case, you can see that this is alpha. Okay, so this is exactly alpha of the Laplace transform of f plus beta of the Laplace transform of g. Right? So why is that the case? Because since the Laplace transform of alpha f plus beta of g is equal to the integral from 0 to infinity e power minus s and t. So up to here at today's lecture, you must be very familiar with this calculation of the Laplace transform. So alpha f of t plus beta g of t, you're integrating against dt. And therefore, this is just the alpha times the integral from 0 to infinity s and t multiplied by f of t dt, right? So plus beta of the integral 0 to infinity s and t multiplied by g of t dt. So that's going to be like very simple. And this is just alpha of the Laplace transform of f plus beta of the Laplace transform of g as functions of s. So here I have kind of kindly ignored that these are function of s, right? So that's that sometimes because of there are two arguments t and s, sometimes we abbreviate a little bit. Okay, so that's going to be the scenario. So that means that Laplace transform is going to transform any linear combination of two functions into the linear combination of their images. So how do you understand this? Well, you understand this from the following picture. Okay, so as I said, you consider the Laplace transform as a mirror. So like the Laplace transform is like a mirror. It is going to take the image. Okay, so take your image and transform to another image. So that's going to be your transformation, right? So that's a mirror. So therefore, you can see that if I take one function alpha, so if I take one function f, right? So they under the Laplace transform in the image, it is going to be transformed to Laplace transform of f. If I take another function g, then in the image, it's going to be transformed to Laplace transform of g. Is that good, family? Now the question I'm asking is that if I connect these two functions by an interval, right? So and consider a certain point inside this interval, then it must be represented as alpha f plus beta of g, because it's a linear combinations of f and g. In particular, this beta is actually 1 minus alpha, right? So if you're familiar with geometry, it's just 1 minus alpha. It's just a linear combination. But let me say I'm going to consider a very general linear combination, alpha of f plus beta of g. Then what's the image of this? Well, the theorem says that alpha f plus beta g is going to be transformed to the information, the linear combination of LF and LG. So that means this is kind of alpha LF plus beta LG. So that's going to be the image of any intermediate point between f and g connected as a line. So and therefore, any linear combination of LF and LG also forms a line. So that actually proves that if you consider this very abstract, so here f is a function, g is a function, I'm just considering the line between two functions. So that's kind of sounds a little bit weird, but it's not strange at all. It's just a linear combination of these two functions, and geometrically it means a line. Is that good, family? Okay, so it is going to transform the lines to lines. It is not going to bend the line. So it's not going to say that I'm going to transform the line to something like a curve. That's not going to happen. Is that good, family? Okay, so that's not going to be happening. Is that good, family? Okay, so you're going to just transform a line to a straight line. Right, so you're not going to really bend this line, but you're going to transform the straight line to a straight line. So that's kind of Laplace transforms. Although it is a little bit strange, and you see that it doesn't map the identity to the identity, right? So it kind of maps the exponential function to such an inverse proportionality hyperbolic function, but it doesn't matter. It is still a linear operation in the sense that it's going to transform the line into the line. In particular, this linearity of this linear transformation explains that geometry. Is that good, family? Okay, this is going to be very important because you can see that it reduces a lot of our calculations. In this example, we don't really have to integrate. We can just use the previous results. And that's going to be very important for our future analysis. Please keep in mind. Okay, so the linearity of the Laplace transforms. Okay, so we say L is a linear operator. Okay, so by operator, it just means the mirror. Okay, so let's say the conclusion is that L is a linear operator. Okay, so let's say linear operator. Operator is just means the mirror, right? So it's the mirror is going to take the image into another image. That means you're making an operation on an image. You give me the image of yourself. After this operation, you get the mirror image. So that's what we say an operator. Or I mean, you can just operator as a mirror. Is that good, family? Okay, so that's about the linearity of Laplace transforms. Okay, so let me show you one more example. Okay, so and which is more like what you're going to see on your upcoming exams. Okay, so let me show you one more example that's more like what you're going to see on your exams. Okay, so here you're giving me, okay, so you can see that's one of the exam problems. It says that if you have this function f of t, okay, so if you have this function f of t, it is going to be like a step function. Can you find the Laplace transform of this function? right? So that what happened here is that the f of t is such a function. So if you look at the graph of this function, how is it going to look like? Well, this is f of t. This is a function of t. So that means you have a pi. Okay, so between 0 and the pi, the function is just equal to pi. Okay, so it's just equal to pi. Starting from t greater or equal than pi, the function is just equal to t. So it's going to be linearly growing. So that function is like a piecewise. Can you consider the Laplace transform of f, or f of s? Well, the Laplace transform of f is going to be the integral from 0 to infinity e power minus s and t multiplied by f of t dt. Right, so you're going to have this. Now, the function is piecewise, which means that the integral is also piecewise. Basically, you have to split the function into its pieces. So that means you want to integrate from 0 to pi, e power minus s and t, multiplied by f of t is pi dt, plus the integral, right? So from pi to infinity, right? So from pi to infinity, e power minus s and t, the function is equal to t and dt. So you want to integrate these two functions. Is that good, family? Now, when you integrate these two functions, the first one is easy to calculate. It's a pi times the integral from 0 to pi e power s and t dt, plus the integral from pi to infinity t times e power s and t dt. So what's this integral? Well, this integral is pi times, so you just want to divide by s, and you consider e power minus s and t. So with a minus sign, where t equal to pi, and t equal to 0, right? So plus the integral from pi to infinity t e power s and t dt. So you want to calculate these two integrals. Now, therefore, if t is equal to pi, well, t equal to 0, so t equal to pi, you're going to have minus pi over s e power minus s multiplied by pi. And when t is equal to 0, it's equal to plus pi over s. Is that good, everybody? Right? So there's the first part of this integral is kind of very easy to be calculated. Right? The first part of this integral is kind of very easy to be calculated. Right? To be calculated. It's just you want to calculate the second part of this integral. Right? So second part of this integral. Now the second part of this integral is the integral from pi to infinity of t e power s and t dt. So what's that integral? Well, it's a t multiplied by an exponential function. So therefore, it kind of reminds you of this method, which we're going to call it integration by parts. Right? So there's a kind of reminds us of this very important method in calculus that we learned in calculus called integration by parts. So integration by parts is going to give you the integral of this term. So that's integral pi to infinity of t e power minus s and t dt. How do you do this integration by parts? Well, the integration by parts is giving you such a very important formula, which just says that the integral of u v prime is going to be the u multiplied by v minus the integral of u prime v. Is that good, family? Right? So that's what we learned in calculus, right? So with that at hand, you can see that this integral from pi, okay, so to infinity of t e power s and t of dt, okay, so t power s and t dt is just equal to, okay, so here I'm going to use u and v, okay, so but I need a u prime, so I will take, okay, so here, if you're not very familiar with integration by parts, you can write it down. So I will take u equal to t. And v prime, so that's v is not going to be e power minus s and t, it's minus 1 over s e power minus s and t. So v prime is going to be just this one. So that's u v prime. So this is t, okay, so therefore you get minus t over s e power minus s and t minus the integral of u prime is 1, so minus 1 over s e power minus s and t, right? So of dt. Is that good, family? The integral is going to be pi to infinity. So here is going to be set t to infinity and t equal to pi. Here we don't have, in this formula, we're not going to have this integrand because we're just dealing with antiderivatives. So you must be very familiar with this procedure in calculus. When you turn the antiderivatives into definite integrals, you have to specify the domain of definition of the two endpoints of this integral. Is that good, family? Okay, so that's going to be giving you a very simple formula. When t is equal to infinity, that's going to be minus infinity divided by s e power minus s multiplied by infinity. And when t equal to pi, it's going to be plus, right? So minus minus is plus pi over s e power minus s pi s. So that's going to be the scenario. And minus two, there are two minuses, so there's a plus the integral from pi to infinity of 1 over s e power minus s multiplied by t dt. S multiplied by t dt. Is that good for everybody? Now that comes the problem. So because you want to have this one, there's an infinity here. There's a multiplied by e power minus infinity here. What is this in this limit? Well, if you assume s is positive, you can see that the exponentially decay always kills the polynomial decay. So basically, it means the limit as you go to infinity of u e power minus s and u is always equal to 0. So therefore, if s is positive, you don't have to be worried about this one. So therefore, you get some very nice results. It's just a pi multiplied by s plus 1 over s. You want to calculate this integral. But this integral is very easy to calculate. It is just going to be equal to 1 over s. Okay, so e power minus s and t, you have a minus sign here. You're going to set t equal to infinity and t equal to pi. You're going to calculate this one. Is that good for everybody? Okay, so that's going to be pi over s e power minus pi multiplied by s, and then minus, let's say, 1 over s squared, where when t is equal to infinity, we're going to have 0 again. And when t is equal to pi, it's going to be pi multiplied by s. So you have two minus signs. So in the end, the whole thing is going to be equal to pi over s e power minus pi s plus 1 over s squared e power minus pi s. That's going to be the scenario. Okay, so that's kind of, but here you can see that during this calculation, we have made a very important assumption that s is to be positive. And this is usually the case. We have to use s to be positive in order to find domain of definition for this function s, f of s. Is that good for everybody? Okay, so that means once you use this result, you take it back into the calculation, you can continue with minus pi over s, e power minus pi s plus pi over s, and then plus this integral is going to be what you have just calculated. It is pi over s, right? So e power minus pi over s, right? So pi over s, and then it's multiplied by what? It's multiplied by 1 over s squared. Okay, so 1 over s squared e power. Okay, so e power minus pi s. So that's, you can cancel this too. So therefore, it's a pi over s plus 1 over s squared e power minus pi s, but you must let s to be positive. That's very important because we have used the fact that s is to be positive in our previous definition. Is that good for everybody? Okay, so that's going to be the scenario. Okay, so that's going to be the scenario. Okay, so you can see that we find the answer, but you must set s to be positive in order to reach a satisfactory solution. In order to reach a satisfactory solution. Is that good for everybody? Okay, so and this is actually what the question is asking for. You can see that it asks you for which values of s is the Laplace transform of f defined, and therefore your answer is that s is positive. So that's kind of sometimes on these exams, it is very important that you specify the domain of definition of the Laplace transforms when you're trying to calculate them. Is that good for everybody? Okay. So let me spend the last 10 minutes. Okay. So let me spend the last 10 minutes on the final problem for today. Okay. So that's going to calculate the Laplace transform of sine AT. Okay. So we're going to just, the problem statement is very simple. You want to calculate the Laplace transform of sinuses of AT. Okay. So that's what's Laplace transform of this function? Well, it's kind of very simple. So you should say that this is 0 to infinity of e power minus s and t multiplied by sine AT dt. So that's going to be a very simple integral. Is that good for everybody, right? So that's going to be a very simple integral. Okay, so let me say sine of AT. Is that good for everybody? But what is this integral? Let me say this integral is I. Okay, so let's say I of a and s. Okay, so let's say I of s. Right, so that's this is your transformation. So let me call it capital F, because this is your Laplace transform. Is that good for everybody? Okay. So how do we calculate this integral? Well, this is something you learn in calculus. Okay, so you have already learned it in calculus. It's just I'm just re-practicing everything, like to show you, remind you of calculus. By the way, if you forgot about your calculus during this class, it is very important that you look back into a calculus textbook. Okay, so let's try to calculate it. Okay, so we're going to say that capital F of s is the integral from 0 to infinity e to the power minus s and t multiplied by sinus of at dt. How are we going to calculate this integral? Well, we're going to use the integration by parts formula. Okay, so we're going to use again the integration by parts formula. Okay, so we're going to use again this integration by parts formula. So that means we're going to treat. Okay, so we're going to treat let's say we're going to treat u as let's say. So let me just make sure that I do everything correct. Okay, so there's going to be another way. Okay, so to do the integration by parts, which can sometimes make your life easier. Okay, so that means sometimes you can write this u v prime as u dv, because dv is like v prime dt. So therefore, this uv prime can actually be thought of as u dv. Right, so and that one is going to be uv minus the integral of v du. So that's another version of so the du is equal to u prime of dt. Is that good, family? Okay, so that's another version of integration by parts formula that might be useful. In particular, for this one, you can see that the integral is 0 to infinity e power minus s and t d of cosinuses of at. Right, so because the cosine derivative is minus sine, so you want to have minus 1 over a in front of your calculation. Is that good, family? Okay, so in that case, you can start to use integration by parts. So it's minus s and t multiplied by cosinuses of at, where you set t equal to infinity and t equal to 0. Because this one is for indefinite integrals, you have to work with definite integrals. Is that good, family? Okay, so once you have this, you're going to subtract. Okay, so you're going to subtract the integral from 0 to infinity. Then you have this uv, so that's going to be v du. So that's the cosinuses of at d of e power minus s and t. So that's going to be the scenario. And therefore, you can see that you're going to have t equal to infinity. So let's say s is positive. Okay, so we always assume s to be positive throughout Laplace transform. In that case, if t is infinity, this exponential term is 0, so you won't have anything. So that's going to give you just 1 over a e power minus s multiplied by t is 1, where t is equal to 0, right? So that's going to be like e power minus s multiplied by 0 of cosinuses of 0. Cosine 0 is 1, right? So, and therefore you don't have anything like this here. You just have 1 over a. Okay, so you just going to have 1 over a in our results, right? So we're just going to have 1 over a in the results. Okay, so here I use the indefinite integrals, but you can actually work with the definite one. Okay, so then it's going to be plus just 1 over a of the integral of this one, right? So this one is like what? Well, e power s and t is going to be e power minus s and t. When you take the d is with respect to dt, so you're going to do dt, and then multiply by cosinuses of at, right? So therefore, you take this derivative with respect to t, you're going to come up with a minus s over a. So you're going to come up with minus s over a in your derivative. Is that good, family? So that's going to be the scenario. So you kind of turn this f of s into another integral. Is that good, family? Right? So is it possible to recover? Okay, so is it possible to recover everything? Okay, so is it possible to recover everything? Well, the idea is that it is possible. Okay, so it is possible for you to come back and recover, right? So when you recover, you're going to just use, okay, so you're going to just continue this calculation. So let me say this is g of s, right? So that means the g of s, you can do a similar calculation, is the integral of e power s and t of cosinuses of at multiplied by dt. So this agrees with our previous assertion that sine and cosine always appear in pairs. Is that good, family? Okay, sine and cosine always appear in pair. when you deal with sine, you also want to deal with cosine. Is that good for everybody? Now for this cosine, you're going to do the same business. Okay, so you're going to do the same business, and so I won't kind of remind you of that one. Okay, so I won't be reminding you of that one, but I will just come back to this answer, right? So for this cosine, I'll leave it to you as a homework exercise that you can easily calculate that again, it is going to be equal to, okay, so it is going to be equal to 1 over a, right? So 1 over a, and then multiplied by e power minus s and t of the sinuses of at, where t is equal to infinity and t equal to 0 minus the integral from 0 to infinity. Then it's going to be sinuses of at, right? So and then d times d e power minus s and t, something like this. Where the sinuses, why there's no minus sign? Well, there's no minus sign because the cosine derivative is sine. So that means you're just going to replace the cosine by the sine here without this negative sign. Okay, so I will leave to you as a homework exercise. Just check by yourself. Now, when t is positive, again, the exponential is 0, but sine 0 is also 0, so you won't have anything like this here. Is that good, family? Okay, so you're going to just have 1 over a of the integral from 0 to infinity sinuses of at, and then e power, right? So e power minus s and t, where you're going to have minus d power minus s and t. We're going to have minus sign here, and then you're going to have dt. So that's going to just give you s over a of the integral of 0 to infinity s and t multiplied by sinuses of at of dt, which can be actually written as s over a. That's nothing but original fs. Is that good for everybody? Okay, so that's going to be the scenario. So in the end, you get such a nice conclusion that capital F of s, according to the first equation, is just 1 over a. Okay, so 1 over a minus s over a, and then multiplied by g of s. But the g of s is like 1 over a minus s over a. The g of s is equal to s over a of f of s. So you're going to have something like this. And this is nothing but an identity. It just tells you that 1 plus s squared over a squared of f of s is going to be equal to 1 over a, from which you calculate the f of s is just equal to a over a squared plus s squared, where s is always positive. That's what we always assume, that s has to be positive. Is that good, family? Okay, so you can see that the only complicacy in this problem is to do two times of the integration by parts, where I leave this integration by parts to you as a nice homework exercise. Is that good, family? Okay, so the conclusion is that we have calculated that the Laplace transform of the sinuses of at is just a over s squared plus a squared. Okay, so a squared plus s squared, but the same thing. Let's say is also equal to a over s squared plus a squared, where s is going to be positive. Is that good, family? Okay, so that's going to say that we have the conclusion sine at is being Laplace transformed to a over a squared. Okay, so a over s squared plus a squared, where s is going to be positive. Now I leave to you as a take-home exercise to practice that Laplace transform of cosinuses of at is equal to what? Okay, try to calculate it from your spare time. Is that good, family? Okay, so that means in this lecture, we have been calculating the Laplace transforms. We'll be introducing this notation of Laplace transforms. Remember, it is always equal to e power minus the universal name s and t multiplied by f of t, the function that you want to transform, you integrate. And in particular, you have to specify the domain of definition for this s. Usually s is to be positive, but it might be even more positive than s larger than a. Is that good, family? Okay. It is very important that you practice the calculation of Laplace transforms in your spare time in order to prepare for the next exam. So here I have listed quite a few exercises on the lecture notes for you to practice how to calculate Laplace transforms. And in our calculation, you can see integration by parts is a very important method that has been used in these calculations. Is that good, family? Okay. So that's what I want to say for today's lecture. Okay, so let's come back to the next lecture. We'll continue with the Laplace transforms.